Hey everyone, it's me again. I will repeat myself for the recording. I'm Lynn Clark and I make code cartoons. And I also work at Mozilla in the Advanced Development Group. So we work on things like Rust and WebAssembly. And this talk is going to be about WASI, the WebAssembly System Interface. So basically, we're creating a standard way to run WebAssembly outside of the browser. I just realized my microphone was not on. So you might not have heard of this before, except I think that you may have. But I'm going to explain at a high level what the why, the who, and the what of this is. And then we can start diving into some of the details of this system interface. So first off, the why. Why would you want to run WebAssembly outside of the browser? And so it's funny. The first time I gave this talk was the day after we made this announcement. So I was actually drafting the talk right after sending out the tweet that had the announcement. And it was at exactly this point in my draft of the talk when that tweet came in from the co-founder of Docker, this one, that said if WASM+WASI existed in 2008, we wouldn't have needed to create Docker. That's how important it is. WebAssembly on the server is the future of computing. Now, this isn't the only use case where running WebAssembly outside of the browser could be helpful. So I mentioned in the previous talk, it's also helpful for Node and serverless and other kinds of applications. But I do want to talk about some of the reasons that across all of these use cases, you might want to run WebAssembly outside of the browser. So some of these reasons are WebAssembly is fast. It gives you these the ability to run code at near native speeds. But it's not just that the code runs fast. It also gives you the fast startup times. So VMs that are built for WebAssembly can start up a lot more quickly than VMs that are running JavaScript. So for example, Fastly is using WebAssembly to handle requests for their serverless platform. And they do this by spinning up a new virtual machine instance for every single request. They can actually instantiate WebAssembly modules in under 50 microseconds. Now for comparison, if you're instantiating a JS module in an engine like V8, it takes about 5 milliseconds. Now WebAssembly is also safe. With WebAssembly, it's easier to keep things secure than it is when you have a binary that's running directly on your machine, as I talked about in the last talk. I'll also talk about this more later. It's also portable, as I mentioned before. You can run it across all of these different devices. And it's also scalable. So it takes a lot less memory to run one of these WebAssembly VMs than it does a JavaScript VM. Now, I mentioned Fastly before. Their WebAssembly runtime only requires a few kilobytes of memory overhead compared to a JavaScript engine. They did compare to V8, and that took up tens of megabytes in comparison. So this means that they can fit tens of thousands of simultaneously running programs in the same process, as opposed to hundreds with a JavaScript engine. So that's why you would want to run WebAssembly outside of the browser. Now let's look at the what of this. Let's look at what exactly WASI is. Now when I was introducing WebAssembly, I talked about how it was an assembly language for a conceptual machine, not for an actual physical machine. And so this is why it can run across a bunch of different machine architectures. WebAssembly is very close to the assembly languages that most machines use. So the runtime only needs to do this small translation from WebAssembly to the actual assembly language that's specific to the machine that's running on. So it goes from this conceptual running on this conceptual machine to running on this the language that runs on the actual machine. Now, just as WebAssembly is an assembly language for a conceptual machine, WebAssembly needs a system interface for a conceptual operating system, not for any single operating system. So this way it can be run across a bunch of different operating systems. And that is what WASI is. It's the system interface for the WebAssembly platform. And now, who's doing this work? So WASI is being standardized in the WebAssembly community group. We've chartered a subgroup to work on it, and you can find more about this in the WebAssembly/WASI repo on GitHub. So if you want to get involved in this, you have a few different options. You can join the CG and work on standardization, or you can also start contributing to one of the implementations, such as WASM time. This is the runtime that we're working on at Mozilla. Or if you have an existing project that you think might benefit from WASI, feel free to get in touch with us to talk that through. So for example, we've been talking with the Node folks about how they could possibly use WASI as a way to make native module development a lot easier and safer. So now that we've covered all of that, let's talk about WASI in more depth. So many people talk about languages like C giving you direct access to system resources, but that's not quite true. These languages don't have direct access to do things like open or create files or open up sockets on most systems. Why not? Because these system resources, such as files, memory, network access, they're too important for the stability and security of the programs running on your machine. If one program unintentionally messes up the resources of another, then it could crash that other program. And even worse, if a program or user intentionally messes with the resources of a program, it can steal sensitive data. So we need a way to control which programs and which users can access which resources. Now, if people figured this out pretty early on, and they came up with a way to provide this control, which is called protection ring security. So with protection ring security, the operating system basically puts a protective barrier around the system resources. This is the kernel. So the kernel is the only thing that gets to do things like create a new file, or open a network connection. And the user programs run outside of the kernel in something called user mode. So if a program wants to do anything like open a file, it has to ask the kernel to open that file for it. This is where the concept of the system call comes in. When a program needs to ask the kernel to do one of these things, it asks using a system call. This gives the kernel a chance to figure out which user is asking to do this. And then it can see if that user has access to it before opening it. Now, on most devices, this is the only way that your code can access the system's resources, through these system calls. So the operating system is what makes these system calls available. But if each operating system has its own system calls, wouldn't you need a different version of the code for each operating system? Fortunately, you don't. So how is this problem solved? Through abstraction. Most languages provide something called a standard library. So while you're coding, you don't need to know what the system you're targeting is and what their system calls are. You just use this standard library as your interface. And then when you're compiling, your toolchain picks the implementation of the interface to use based on which system you're targeting. So this implementation will use functions from the operating system's API. And that means it's specific to the system. And this is where that system interface comes in. It provides that abstraction layer over that. So for example, PutC being compiled for Windows could use the Windows API to interact with the machine. And if it's being compiled for Mac or Linux, it can use the POSIX APIs instead. This poses a problem for WebAssembly, though. With WebAssembly, you don't know what kind of operating system you're targeting, even when you're compiling. So you can't use any single operating system's system interface inside of the WebAssembly implementation of the standard library. So this is why we need that system interface for the conceptual operating system, not any single operating system. But we don't have that system interface, or we didn't have that system interface before. But there were already runtimes that could run WebAssembly outside of the browser, even without having the system interface in place. So how were they doing it? And we can take a look at that. So the first tool for producing WebAssembly was unscripted. It emulates a particular operating system interface, POSIX, on the web. And so this means the programmer can use functions from the C standard library. To do this, Mscripten created its own implementation of that standard library. And this implementation was split in two. So part of it was compiled into the WebAssembly module, and then the other part was implemented in JS glue code. And then the JS glue code would call into the browser, which would then talk to the operating system. Most of the early WebAssembly modules were compiled using unscripted. So when people started wanting to run WebAssembly outside of the browser, they started by making unscripted compiled code run. So that meant that these runtimes need to create their own implementations of all of this JS glue code. There's a problem here, though. The interface provided by this JS glue code wasn't designed to be a standard, even really a public interface. That wasn't the problem it was trying to solve. So for example, for a function that would be called something like read in an API that was designed to be public-facing, the JS glue code instead uses underscore system3, which var args. So the first parameter, which is an integer, is always the same number as the number at the end of the function. So in this case, it would be 3. And then the second parameter, var args, are the arguments to use when calling that. And it's called var args because you can have a variable number of them. But WebAssembly doesn't provide a way to pass in a variable number of arguments to a function. So instead, the arguments are passed in via linear memory. And the problems with that are that it's not type safe, and it's also slower than it would be if the arguments could be passed in using registers. So this was fine for unscripted running in the browser. But now runtimes are treating this as a de facto standard, implementing their own versions of this JS glue code. So they're emulating an internal detail of an emulation layer of POSIX. And this means that they're re-implementing choices, like passing in arguments as heap values, that made sense based on unscripted's constraints, but don't apply in their environments. If we're going to build a WebAssembly ecosystem that lasts for decades, we need solid foundations. So this means our de facto standard can't be based on an emulation of an emulation. But what principles should we apply in designing the standard? So I talked about the 2 important principles of the web in the last talk, portability and security. We need to maintain these key principles as we move to outside the browser use cases. So as it is, POSIX and Unix's access control approach to security don't quite get us there. Let's look at where these fall short. And we'll start with portability. POSIX provides source code portability. So you can compile the same source code with different versions of libc to target different machines. But WebAssembly needs to go one step beyond this. We need to be able to compile once and run across a whole bunch of different machines. So we need the binary to be portable as well. This kind of portability makes it much easier to distribute code to users. So for example, I mentioned Node in the last talk. If Node's native modules were written in WebAssembly, then users wouldn't need to run Node JIP when they install apps that are native modules, and developers wouldn't need to configure and distribute dozens of binaries. Now let's look at security. When a line of code asks the operating system to do some input or output, the OS needs to determine if it's safe to do what that code is asking. And operating systems typically handle this with access control that is based on ownership and groups. So for example, the program might ask the operating system to open a file. A user has a certain set of files that they have access to. And when the user starts that program, the program then runs on the behalf of that user. So if the user has access to the file, either because they're the owner or because they're in a group that has access to it, then the program has that same access to it. This protects users from each other. And that made a lot of sense when the early operating systems were being developed. Systems were often multi-user, and administrators were controlling what software was being installed on these. So the biggest threat that you had was that other users on the same machine were going to take a peek at your files. That's changed though. Systems now are usually single user, but they're running code that pulls in a lot of other third-party code that's of unknown trustworthiness. So now the biggest threat is that the code you yourself are running is going to turn against you. So for example, let's say that you're using a library in your application and it gets a new maintainer, as often happens in open source. Now that maintainer might have your interests at heart, or they might be one of the bad guys. And if they have access to do anything on your system, so for example, open any of your files and send them over the network, then their code can do a whole lot of damage. So this is why using third-party libraries that can talk directly to the system can be dangerous. WebAssembly's way of doing security is different. So as I mentioned in the last talk, WebAssembly is sandboxed. That means that the code can't directly talk to the operating system. But then how does it do anything with those system resources? The host, which may be the browser or might be a WebAssembly runtime running outside of the browser, puts functions in the sandbox that the code can use. And so this means the host can limit what the program can do on a program-by-program basis. It doesn't just let the program act on behalf of the user calling any system calls with the user's full permissions. Just having a mechanism for sandboxing doesn't make the system secure in and of itself. The host can still put all of the capabilities into the sandbox, in which case we're no better off than we would have been otherwise. But at least it gives hosts the option of creating a more secure system. In any system interface that we design, we need to uphold these two principles. Portability to make it easier to develop and distribute software, and we also need to provide these tools that allow hosts to secure themselves and the users. Given these two key principles, what should the design of the WebAssembly system interface be? That's what we're going to figure out through the standardization process. We do have a proposal to start with, though. So first, create a modular set of standard interfaces, and start with standardizing the most fundamental module, which is WASI core. So what would be in WASI core? WASI core will contain the basics that all programs need. So much of the same ground as POSIX, including things such as files, network connections, clocks, and random numbers. And we'll actually take a similar approach to POSIX for many of these things. So for example, we use POSIX's file-oriented approach. So where you have system calls such as open, close, read, and write, and then everything else basically derives from that. But WASI core won't cover everything that POSIX does. So for example, the process concept doesn't really map very clearly onto WebAssembly. And beyond that, it also doesn't make sense to say that every WebAssembly engine needs to support process operations, like fork. But we also want to make it possible to standardize fork. So this is where that modular approach comes in. This way we can get good standardization coverage while still allowing niche platforms to use only the parts of WASI that make sense for them. So languages like Rust will use WASI core directly in their standard libraries. So for example, Rust's open is implemented by calling WASI path open when it's compiled to WebAssembly. For C and C++, we've created a WASI sysroot that implements libc in terms of the WASI core functions. And we expect compilers like Clang to be ready to interface with the WASI API, and toolchains like the Rust compiler and unscripted to use WASI as part of their system implementations. And in fact, Rust already does have support because of Alex Creighton, who's absolutely fantastic. So how does the user's code call these WASI functions? Well, the runtime that's running the code passes the WASI core function in as imports. And this gives us portability, because each host can have their own implementation of the WASI core functions that's specifically written for their platform. So WebAssembly runtimes like our WASM time and Fastly's Lucet, or Node, or even the browser can have their own implementation. It also gives us sandboxing, because the host can choose which WASI core functions to pass in, so which system calls to allow, based on which program is running. So this preserves security, but WASI actually gives us a way to extend the security even further. It brings in concepts from capability-based security. So traditionally, if code needs to open a file, it calls open and passes in a string. And that string's the path name to the file. And then the operating system does a check to see if the code has the permissions based on whichever user is running that program. With WASI, if you're calling a function that needs to access a file, you have to pass in a file descriptor, which has permissions attached to it. So that could be for the file itself or for the directory that is containing that file. And this means that you can't have code that's randomly asking for access to open etc password. Instead, the code can only operate on the directories that are passed into it. So this makes it possible to safely give sandboxed code access to more different system calls, because the capabilities of those system calls can be limited. And this happens actually on a module by module basis. So by default, a module doesn't have any access to file descriptors. But if code in one module has a file descriptor, it can choose to pass that file descriptor to functions that it calls in other modules. Or it can create more limited versions and pass those to the other functions. So the runtime passes in the file descriptors that an app can use to the top-level code. And then the file descriptors get propagated through the rest of the system on an as-needed basis. And this gets WebAssembly closer to the principle of least authority, where a module can only access the exact resources that it needs to do its job. So these concepts come from capability-oriented systems like Cloud API or Capsicum. One problem with capability-oriented systems is that it's often hard to port code to them. But we think that this problem can be solved. If code already uses system calls like open_at with relative file paths or fopen, compiling the code will just work. Now, if code uses open and migrating to the open_at style of doing things would be too hard, WASI actually provides an incremental solution. With lib pre-open, you can create a list of file paths that the application legitimately needs access to, and then you can use open with just those file paths. So what's next? Well, we think that WASI core is a really good start. It preserves WebAssembly's portability and security and provides for a solid foundation for this ecosystem. But there's still questions that we'll need to address after WASI core is fully standardized, or while WASI core is being standardized. And those questions include things like asynchronous I/O and file watching and file locking. So this is just the beginning. If you have ideas for how to solve any of these problems, please do join us. I want to thank my collaborators on developing this talk. So these are Dan Goman, he's the lead developer on WASI, our WebAssembly runtime WASM time. Till Schneidereit, who you saw earlier tonight, he leads our developer technologies team focusing on Rust and WebAssembly. And Luke Wagner, who's one of WebAssembly's creators and a driving force in many of the proposals that I've talked about tonight. So thank you to all of them, and thank you all for listening. And if I'm not mistaken, we will have a Q&A after this one as well.
Sure. But if you have specific questions to this talk, we can have a few questions right now. So, questions?
So would you like to come back up?
Sure. Yeah.
Hello, thank you for the talk. It was very good.
Thank you.
Extraordinary. Given the background here. Yeah, my questions would be about WASM. So you support several backends, crane lift. So does it now compile natively? And then the other backend, LLVM. So how do you see the future on LLVM? Are you still supporting it? Is it like competitor? What's your opinion on that?
So LLVM is not a competitor. The Dan Goman, I should have mentioned, he actually wrote the WebAssembly backend for LLVM as well, and was one of the original LLVM core team members. So we're cool with LLVM.
So what about the future of crane lift?
What about the future of crane lift? It has a bright future. We're working on it. Fastly is also contributing to it. They gave us a lot of great optimizations. We are now working on making it even faster. We're working a lot on the register allocator. And we have some, we're working on also how we can create extension points so that it can be used for as many use cases as possible without making compromises. So that's what we're working on for crane lift.
So will there be a safe libc WASI interface somewhere for Rust?
A safe libc WASI
Yeah, just seeing in
interface.
the code it's still marked as unsafe, so you're probably executing C code.
Oh, I actually don't know if I'm.
So that WASI doesn't really give you that. Unsafe in Rust is not so much about sort of effects in the outside world. I mean, that in part also, but it's also about saying, I know how to handle this pointer here, for example. Trust me on this. And that pointer can be in the linear memory heap. So unsafe doesn't necessarily mean exploitable in the outside world, but also just inside your sandbox. You still need to be able to use unsafe code, for example, to create doubly linked lists in Rust. That won't go away.
So we trust the code. Okay, last question. So how is Mozilla, or how are you related to the V8 team here? Are they supporting WebAssembly and?
We're buddies.
We
love seeing them. No,
I expect that.
it's really true. That's one of the things I love about the WebAssembly work that's happening in the community that I get to be a part of. We meet up face-to-faces. It's always a fun time. We go out to fun dinners together. It's a pleasure collaborating with them.
Okay, that's nice. Thank you.
Okay, let's have maybe 5 minutes break if you want. And then we will continue with the AMA session where you can ask any questions like this.
I don't need a break. I don't know if other people need a break.
Do you need a break?